Okay, so we are glad to have Peter Koroteev currently from UC Berkeley. He will tell us about q-Opers, and so then hopefully we will know what they are and what they are good for. Peter, please.
Yes, thank you, Jan. Thank you very much for invitation. And probably that's an accurate description of what's about to happen in the next hour or so. So, which means please ask questions and interrupt at any time. So I just see the slides have been posted. There's a link, you can download them. And if you want to go ahead and ask the questions ahead of time, that's fine too. So let me begin with expressing my support to people of Ukraine. As you can see, the title is, in theme of Ukrainian flag. So we, of course, condemn all the actions by Russian military and what's going on in the region. And we'll hope that the conflict will be resolved soon, and we can get back to normal life. We can, do mathematics instead of thinking about horrible things. So I hope you'll join me in this support. So I have been working for the past several years with mostly with these people, Anton Zeitlin, Edward Frankel, and Daniel Sage. So Anton and Daniel, they are a faculty at Louisiana State University, and I just visited there last month, and Ed Frankel is here in Berkeley. And so it's a program of works which are trying to connect several aspects of algebraic geometry, representation theory. So in particular, sort of one of the goals is to understand geometry behind quantum integrable systems. So people have been studying quantum integrable systems for a very long time, but then like most of the work has been done on like the formal integrability aspect of things, and the geometry has not been discussed in very detail. So I hope at least I hope to explain you that part in my talk. So like so in sense, what if you want a kind of not a kind of slogan kind of answer, what is a q-Oper? So for us, q-Oper is it's an algebra geometric object that underlies the a spectrum of quantum integrable system. So it's a classical object. Essentially, it's a bundle with some sub-bundle with certain properties, which replicates the properties of that quantum integrable system, or as well as other things. So yeah, like I'm not going to talk about all these papers. So probably most of the discussion will be along the lines of this paper over here, and maybe that paper over there, depending on time. So let me mention some motivational points. So one of the motivations is studying of quantum integrable systems. This is sort of I've been working on them for quite a while now from different perspectives, including string theory and just integrability itself. And we have some papers on, so following the works by Andrei Okmenkov and collaborators, we studied how these quantum integrable systems arise in the description of equivariant quantum K-theory of q-varieties and other symplectic resolutions. Then sort of from physics world, there's this famous BPS CFT correspondence by Nekrasov and Shetashvili. And in geometric language, it relates basically these two things, right? It's like the connection of quantum geometry, like quantum K-theory of some spaces, with a spectrum of integrable systems that arise from them. So I hope I'll mention that in the beginning. Then sort of more formally, what we're doing is so what I'll be describing today is a certain classical, like critical level limit of geometric Langlands. And this is a sort of difference version. You can call it q-Langlands correspondence, when instead of d modules, you have difference d modules, right? Instead of local systems, you have some, difference analog of that. And then, yes, like in the q version, you're probably aware that the Langlands correspondence, like the full categorical statement, is actually have similar looking category on both sides, right? And what you're doing, you're just rotating some parameter. Yeah, and finally, so the most recent work that is not published yet is along the lines of the so-called Odeim correspondence. So here you would study on the ODE side, you have some, well, ordinary differential equation with a singularities, with a like apparent singularity, like simple pole. And then on one side, you would study monodromy data of the fundamental space of solutions of this ODE. And on the other side, the IM stands for integrable model. It turns out that if you look at this in the right way, the monodromy data of this ODE encodes in itself equations from the integrable system. So this the equation that I'll be writing many times today, the so-called QQ system, arises as well. You can kind of deduce it from monodromy of those equations, right? And also q-Opers, essentially they'll be related to monodromy matrix of those ODEs. Okay, so that's kind of it. Any general questions at all, or
well, it's too many unknown words, so then...
Yeah, of course. Yeah, I don't expect to. Yeah, but like, I mean, if you want to ask something.
I'm afraid that if I start to ask questions, so you will not be able to talk, to give you talk. So then just go on.
Okay, good. So then it has to go. Good. So let's start from the definition, right? So consider. So first, talk about SL2 Opers. So Q is a complex parameter, right? And then consider vector bundle of degree 2 of a CP1. And then there's this map M sub Q, which just multiplies, like in some trivialization, it multiplies Z by that Q, right? And then, so that induces grading, right, on this vector bundle. And then there's a map, linear map between vector bundles E and the pullback of E under this map MQ. Okay?
Can the absolute value of Q be equal to 1?
In principle, yes. Yeah, like at this point, there's no problem.
I'm afraid it's not always induces a grading, so then it's
okay, sort of like but you can still define this map, right? So
yes, but the geometry will be completely different if absolute value of Q is equal to 1. So
yes, okay. So if Q is a root of, right, so if Q will be root of
not necessarily a root of 1.
Not even like some fraction, like just some point on the unit circle. Yeah. Okay, so let's proceed along the formula. So let's assume for now that it's not root of unity and not absolute value is equal to 1, and then we'll see in the formula below where this can cause a problem. Yeah. So for simplicity, assume that this is not the case, as Jan suggested. And then let's say we pick some trivialization. So like some of the formula will be for generic GLN case, but then I'll specify them for SL2. So say A of Z is this matrix from the loop group, from the algebra, excuse me. So GLN of C of Z. And then if you want to change this trivialization, this linear map, right, will undergo what is called a Q gauge transformation, right? So you would take I'm sorry, there's a typo here. No, never mind. There's no type. It's fine. Yeah. So and then upon trivialization, so A goes to G of QZ, A of Z times G inverse of Z.
Right, Peter, so, I'm not that much of a physicist, so then I might be a little bit more pedantic. So first of all, when you say trivialization, you mean trivialization at the generic. I mean, not every vector bundle on P1 is trivial, as you know. Yeah, so you consider it's rational. Okay, so
yeah,
then
right. Yes. So,
basically, is it the same as just equivariant sheaf on?
Yes, this one. So A will be a section of this sheaf.
Okay.
Yeah, that's right. So I want my gauge transformations to be rational functions. Yes, so that's why it's important that I live on P1. So the first definition is the definition of the Q connection. So GLN comma Q connection over P1 is a pair of bundle and this map A, where E is a locally trivializable bundle of rank N for GLN, and A is a section of this sheaf, right? Such that A is invertible, right? So it lies in GLNC, C of Z. And then if you want to have SLN connection, you just make sure that the determinant of this connection of this matrix is equal to 1. So that's the Q connection, right? So so think of it as a linear map from here to here, and then there's an associated difference equation. So you can basically take a section of the bundle, right? And then you can either make a Q shift, right? So calculate, something like S of QZ. And on the other hand, you can act on it with S of A of Z times S times S.
So may I ask you a question, since you're allowed to ask questions? So since you mentioned some interesting words like Langlands correspondence on the previous side, so why do you consider just the connections? Because I mean, clearly there is a notion of meromorphic QD module, and so it's a little bit more general.
Yeah. So we'll introduce some singularities, like we will. So when you say meromorphic, it's a meromorphic connection, right? So meromorphic.
No, not meromorphic connection. Meromorphic QD module, like the ordinary D module on the curve. It's not necessarily a bundle with connections. Similarly, when you introduce this equivariant structure, which severely restrict your curve, it's basically P1 only. Yeah, then you still have a possibility to introduce analog of the delta function. So it's kind of
like at the origin, like, or infinity, zero infinity. So.
Well, yeah. So then I don't know. I mean, it's up to you, of course, but there is a.
No, I mean,
these objects were considered at the beginning of 90s. Claude Sabach developed the theory of QD modules in any dimension. He did not compactify. He considered something on the torus, like if you throw away fixed points, it will be C star. So then I'm just trying to understand, is it something new or it's something which I already saw many years ago? It's okay.
Well, so I mean, I haven't introduced the Oper condition yet. So far,
okay, just two different. Okay, good.
So far, it's very, very general. You can sort of, enrich it with all kinds of structure. Then that's what I'm about to do. So now let's talk about Opers. So what's an Oper? Right. So first of all, what does the word Oper mean? I think Jan probably knows the answer, right? It's also written in Frankie's popular book. Right, so it says essentially Oper is a short for operation, right? Operational sort of, but it's meant in some very specific sense, right? Anyhow, so let me give an example for GL2, or an SL2. So GL2 Oper on P1 is a triple, so it's a bundle connection and a sub bundle. It's a line sub bundle where E sub comma A is a Q connection from the previous slide, and then L is a line sub bundle such that the induced map from L into induced map L a bar from L to E mod LQ is an isomorphism, right? So this is the Oper condition, that there's a isomorphism between a sub bundle and the factor bundle, if you think of them as vector spaces.
It's pretty formal. There is some.
I'm about to write down the formula. Yeah. So let's see how this plays out in some coordinates, right? So say S of Z generates L, right? It's a one-dimensional vector space, right? And then this is what this condition means, that you take vector S of Z, so it's a two-component vector, you act on this with a 2x2 matrix, and then in general, this vector will be rotated, right? By GLN transformation, it will rotate this and maybe stretch it. And the claim is that if you wedge it with S of QZ, you're not going to get zeros. In other words, this vector and that vector are linearly independent. Okay.
Well, I don't know. Formally, you introduce some object, but there is notion of Oper due to Billinson and Greenfield. and
it's the
without the
same
letter
thing.
Q. Yeah, but
Right, because
probably
they
it's
didn't have
not geometric, because this Q equivariant structure, it's kind of, it requires some time to absorb. But probably more people in the audience know what is a bundle with connection on a curve. So maybe you will explain what's Oper without Q is, and so then it will be easy to understand what this Q.
Well, once I have this construction, you can take some scaling limit when Q goes to 1, but it's not just Q to 1. You need to preserve like the first term here, like the definition of the Oper without Q is similar, right? So you have some short exact sequence, like this one, right? So basically, it's so the objects are the same. Right? This is embedding the sub bundle, right? And then factor bundle, and then so like the you just don't you don't really have so Q grading is definitely new here, right? And it's kind of important, but then, well, you know what? Let me proceed a little bit further, and then maybe I can say a comment on that, right? So at least I want to have a definition. So it's we're not done yet. So for now, let's just stick with. In some sense, I think even Q objects are somewhat simpler than non-Q because of the thing.
Well, you're the speaker.
Okay, good. So yeah, good. Right now, and then so as Jan wanted, I want to have more structure. So now I want to introduce regular singularities at some positions, which are different from 0 and infinity, right? And then for each singularity, I also assign weight, K1 through KL. And that's what this thing does. So on Oper with those singularities and with this data is a meromorphic SL2 q-Oper, such that we allow this induced map, this isomorphism, to fail at those points, right? So, and not only we allow this to fail at these points, but also at certain multiples of Q. So that's where the sort of Q gradient kicks in. So think about it this way. So this is your CP1 without 0 and infinity, and then it's really like kind of a C-star action, right? So you would take one of the singularities and then multiply it by Q squared, and Q to some integer power, and then like there's like a whole tower of points where the isomorphism fails. Sort of where these sort of two vectors become linearly dependent. Okay, now so those guys are called weights, and then so and then one more piece of data. Okay, let me move this window here. One more. Oops, sorry. One more piece of data is the Z twistedness condition. Now, as I showed you before, the Q connection can be gauge transformed or Q gauge transformed like so, right? And then we say that this Oper is Z twisted if we can transform it to a diagonal matrix, constant diagonal matrix Z. Okay.
So may I ask you, I mean, so basically your Z just belongs to an orbit of this rational matrix valued function. So it's some question about classification of this rational A of Z.
So if H is a maximal torus, it's the constant part, right?
Yeah, but the formal classification, if I will ask the question which people like Ginsburg and Baranovsky asked many years ago, so about the formal classification. So basically, it's the same as semi-stable. If you replace A of Z by the formal series, I don't know, it's zero. So just you ignore.
If it's a series, it's a problem, right? So you have to. I mean, you are not guaranteed to diagonalize it by rational function.
Just you take GLN with coefficients in the Laurent series, and so everything makes sense on the right-hand side. G of Z.
If there's a Laurent series, I think you need to take a disk, right? So something non-compact.
Laurent series is purely formal thing. So anyway, it looks like you didn't read the paper. You just invented your own definition. Okay, good.
I mean, okay. So what we did, we looked at Billings and Drinfield's paper. They have a definition for Oper, and then to come up with a Q analog, it's very straightforward, right? So it's just the basically it's this condition over here. Well, okay, but the classification of what? I'm sorry, you said you asked about.
It's okay. Yeah, go ahead. So let me not to kind of spoil.
Okay, maybe we can talk about this later. Okay. Other questions? Okay, I'll have more people in class. Okay, and then one more piece of structure that we need to actually be able to write some formula with those opers is the Miura q-Oper. Yeah, so as Jan is constantly mentioning, all of what I'm saying exists for what is called differential opers, like normal opers, non-q. Now, what's Miura oper? It's a quadruple of data, right? So now we have, well, stuff that we had before, and also we have another sub-bundle which is preserved by the Q connection. So in other words, say for SLN at SL2, the connection matrix has upper triangular form or lower triangular, depending on which sub-bundle you choose. So let's see how this plays out. Choose in some trivialization if L is generated by this vector here. So I call those components Q plus of Z and Q minus of Z. Then this twist element, then the matrix Z, which we call twist element, is a diagonal matrix with eigenvalue zeta. And then the singularities of the Oper, which I remind you appear in this definition here, right? This polynomial lambda, it parameterizes those singularities. And if you put this all together, then the q-Oper condition, which I remind you looked like this. So it's a determinant of a Z of the 2x2 matrix. And now it's not equal to 0, but it's equal to this polynomial lambda. So it's non-zero everywhere except those singularities, right? And if you write this down as, you know, spell it out, open up the determinant, you'll get this thing in the left and lambda on the right. And this is an example of what is called the QQ system. Right? You should think of it in general as a functional equation on this polynomials Q plus and Q minus. So in my example here, in this first part of the talk, well, those will be polynomials, but in principle, they can be entire functions of Z. They can have poles. There's a whole variety of possible solutions of this QQ system. So, and then, yeah, so just to connect it with other stuff that we knew from integrability before. So let's parameterize those polynomials explicitly. So we can always make one of them monic. So the coefficient in front of Z to the top power is equal to 1. And then say WK are roots of Q plus. And then there's this standard trick that you would evaluate left-hand side and the right-hand side at those roots. So that would kill this term, right? And then you can make a Q shift or a Q inverse shift and evaluate this again. So that will kill that term. And then you divide the first equation by the second equation. And you can see that in this way, the Q minus, right, the dependence on polynomial Q minus, which I didn't even write down, disappears. And you get this equation, which you can write down in this form, right? And this is the famous beta ansatz equation for the XXZ spin chain on L sites, L spins with M excitations in the presence of twists and anisotropies. Yeah, which is it has been studied in spin chain, like in integrability literature for a very long time, since Hans Bethe, right, 100 years ago. Questions here? Okay. So yeah, now I mentioned in the beginning the difference equation. So let me show how this difference equation looks like. So the Miura Oper looks like this. There's invariant subspace, meaning that there is one of the elements is 0. So over here, so it's a diagonal, it's an upper diagonal matrix. And then the Z-twisted condition looks like so, and you can find explicitly this diagonalizing element V, which, as you can see here, also takes values in positive Borel subalgebra, right? So it's upper triangular matrices over here. So not only can diagonalize A to this diagonal element, but they can also achieve it by elements from Borel subgroup, right? Not only from not just a G of Z, but actually B plus of Z. So it's a stronger constraint. And then you can figure out explicitly what its coefficients are, and the QQ system, and then so the difference equation right over here. So this del Q of S equals AS. It's since I told you this is a 2x2, it's a 2-component vector. So we can write, and then the matrix A is upper triangular, so we can solve it for the second component, substitute in the first equation for the first component, and that will give us the second order difference equation. So which looks like this. There's a kind of del Q squared, which shifts by Q squared. And then there's a linear coefficient and a constant term. And this T of QZ is also known in integrable literature as an eigenvalue of the transfer matrix, well, like the transfer matrix operator. So usually, if you hear talk by a physicist about Opers or q-Opers, well, there are not too many talks about q-Opers in physics, but anyhow, they would write down this operator. Now, if you ask what happens if you take limit q to 1, if you take limit q to 1, so this will become essentially a holomorphic Schrodinger equation. It will look like del z squared plus some potential. And then this potential here has certain poles of degree 1 and degree 2. But sort of I'm explaining the geometric structure underlying this expression. Okay. Questions? Somehow Jan stopped asking questions.
Yeah, you see, so you are the speaker, so I cannot kind of, you have kind of as a main motivation, probably you assume that we know what are the Opers and what are they good for.
No. Like, so I wrote everything.
I don't know why should I be happy that that better considered some model almost 100 years ago. If there is no mathematical structure
I'm explaining the mathematical structure. So in fact, the whole goal
what's a structure? What is the structure? So okay.
The structure is that the Opers, right? So there is a system of equations which is called QQ system, right? And then I'm explaining geometric structure behind those.
So what's a geometric structure? I do not see. I see some equation. That's it.
No, the Q functions are the components of the section.
Okay.
So
so I should tell you that the notion of Q difference equation, it's not quite geometric unless you reduce to the elliptic curve. Then you have some coherent shift on the punctured elliptic curve. Yeah, your Q doesn't have absolute value.
Why can't I stay on the P1? I want to stay in rational world. Why do you want elliptic curve?
So because you have an equivariant structure on your shift, so you can reduce it to the elliptic curve. So then, and probably your Oper is q whatever. It's some. It can be spelled out in terms of coherent sheaf on the elliptic curve with some additional reduction for
to Borel,
yeah, something like that, which probably means choosing a line. So anyway, it will be something geometric, but so far you are writing formulas, and so this kind of a capacity, at least of my brain, is limited. So if
so I'll give you a full generics construction, well, without formulae for any
not
group.
a question. First question is not the construction, but you promised to say why. So what's good with these Opers? What problems will you solve maybe later using this strange definition? What they're good for?
Well, so they would. So one application is understanding the geometry behind this integrable systems and some generalizations. Another application is.
But for you, integrable system is just a collection of very concrete integrable, very concrete models with attached.
So there are two types of models, right? So one of them is comes from well, one of them are many body systems like algebra, right?
So I don't know. I know who algebra. I heard these words, algebra Moser, but what is it? I mean,
yeah. Okay, I'm coming to that. Okay, good. So let me explain that part then. Yeah, so
yeah, but just before you come, so let me just make it. So there will be several integrable systems which are just some concrete models with names attached, like Böte, algebra Moser, maybe Gaden or something, somebody else.
Yeah, but like, so
it's not a class. It's not kind of a class like, you know, differential equations. It's a huge modules. It's kind of a huge class.
No. Like so what I'm saying is that these sort of Opers, like the q-difference equations that arise from Opers, are in a sense they form a class, and it's a much bigger class than say that you get from, say, you know, equivalent quantum K
yeah,
theory.
But ordinary Opers, if I remember correctly, they were invented to describe some spectral properties of large classes of integrable systems.
Yeah. So that I'll mention
these large classes. I see just
it's coming. Okay, so I think you need to be a little bit more patient. Okay, so I'll explain that part. Yes, I promise to explain that part. Yeah. So that's will be first application, and then second application will be a relationship to cluster structures like Fomin-Zelevinsky and stuff like that. And the third is the Odeim correspondence. Okay, so let's talk about classical integrable systems. Are there any other questions about what was here? Okay, so first example of a so Jan mentioned spectral curve. So before giving the full definition, let me give you an example of a two-body system. So if you take the q-Oper, right? So I remind you that we have a section with two components, component functions, q plus and q minus, right? And then if we choose those polynomials to be of degree 1, and then we write down the Oper condition, which looks like this: S of qz wedge z times S of z equals lambda of z, which in this case is just a polynomial of degree 2. And then you calculate the determinant, you'll get a degree 2 polynomial in z on the left and on the right. And you can also show that this thing on the left is written as a sort of spectral curve for, in this case, it's a trigonometric Roisinart-Schneider model, right? So LTRS, it's a lax matrix for TRS model, because I see there are some experts in integrability in Zoom. So this is lax matrix. And the
it's not talk for narrow experts, you know.
No. Yeah, it's only like the first 5 pages. Yeah, it's kind of like the general geometry is coming. Don't worry, it's not a talk for narrow experts. Yes. And then the coefficients, you can see that the coefficients in front of well, z and z to the first power and z and the constant are the Hamiltonians of this integrable system. So in other words, the q-Oper condition specified for the simple polynomials, like, so it's a very simple Opers. In principle, you can have it much more complicated, but like for the simplest one, it will give you the spectral, well, the spectrum, the energy spectrum of this two-body integrable system. Okay, I see there's Tom Sutherland in the room. So Tom, do you have a question, or does it look okay to you? Okay, good. So what are they in general? So these Hamiltonians appear from in so-called Kaloger-Moser space. So we take so let V be an n-dimensional vector space over C, right? And then M prime is a subset of GLV cross V cross V star. So and then it consists of elements M, T, U, and V, which obey this relation. So
what is V in the power T?
Transposed. It's
T in the left-hand side is not transposed. It means something else, right?
that is correct. Yes. T is here. It's an element. It's a matrix, right? So M and T are matrices. U and V are vectors. So the condition tells you that the Q commutator of M and T is equal to the matrix of rank 1. Okay. And then so we subject this M prime by the conjugation of GLN. All right, so we can do it like this, like so, and then we quotient by this action, and this quotient is called the Kaloger-Moser space.
So what is it? Is it algebraic variety? Is it
it's
singular? Is it normal?
It's a stack. It's an algebraic stack.
So it's an algebraic stack. Okay, good.
Yeah. Then so you can also understand it sort of topologically as a character variety of the torus with one puncture, right? So you would have a modular space of flat connections on the torus, and then the A and B will be A and B cycles of the torus, and C is the cycle around this puncture with whose eigenvalue is Q. And then once it
looks rather, at least it contains an open part, which is a symplectic manifold. So it's symplectic because your Q is fixed. Yes. So then, okay, good. So then it's singular symplectic variety.
Yeah? That is correct. Yes. And then the integrable Hamiltonians of a TRS model would come from calculating traces of various powers of T. So you can pick a basis where M is diagonal, and then traces of T would be the TRS Hamiltonian. So an example of such Hamiltonian for two particles is given here. So if
Peter, I'm confused a little bit on this slide. So this M and T, they are what? I would say that this should be the monodromies, but you have the additive relations between them, not multiplicative. So
I'm sorry, guys. Give me 1 second. Give me 1 second. I'll be back in 5 seconds.
Okay. Yeah. Okay, so.
No, I'm sorry. It's fine. I was checking so that my daughter came from school. Yeah. So what was the question?
The question is that this character variety presentation, it's sort of a Betti side. You consider representations of the fundamental group of the puncture torus. This is in the left, in the right corner, but this additive presentation with q mt minus t, it's look like a drum side. So or what? What m and t?
You're implying in this. So they're not literally A and B. That's right. So
They're certainly not A and B because they satisfy different, but what they are, how they are related to A and B.
I mean, you can, I guess you can write out some explicit relations. I'm not sure how explicit they are. So, well, I can show you that Hamiltonians you get from this approach and from this approach are the same. So yeah, like I don't think it's like I said, these are just two different ways to get the same thing. And so if you more like this character variety part, you can do it. If you like more algebraic construction, you can do that as well. Yeah, I'm not going to give you the formula how M relates to A, for example. It's not.
Is it transcendental relation? Does it involve?
Yeah, I think it's a transcendental relation. Yeah. Maybe for for 1 degree of freedom you can do it, but not for. I don't know how to do it for like SLN or something.
Okay.
Good. Yeah. So we have that, and then the. Okay. So let me skip some stuff. So the duality from integrable systems. Okay, let me just go quickly here because folks don't seem to be interested. So there's a connection between classical systems like trigonometric Rosen-Snyder, so those models that appear from the geometric construction, and the quantum spin chain. And the way this correspondence works is that you would look at the I don't know how to remove this. Actually, yeah, I know. Yeah, so you would look at the solutions of this beta-like equations for the spin chain and the energy level equations for the trigonometric Rosen-Snyder model. And then there's a match, basically this space set of solutions of these equations in bijection with set of solutions of those. And there's essentially the dictionary, right? So the coupling constant in Calogera space, in Calogera Mother sense spaces, actually it should have been Q, I'm sorry. Q here. Well, I mean, okay, Q is H bar. So an H bar on this slide, because it's a Planck constant, is the same as Q in my q-Oper. So coupling constant is relative to the Planck's constant, and then this twist eigenvalues and equivariant parameter eigenvalues are related to coordinates of those particles and the energy levels. So more precisely, the symmetric polynomials, elementary symmetric polynomials of those variables are energies of Terrace Hamiltonians. Yeah, and we knew this duality before, like from, well, it's been known in the literature for some while. So if we generalized it to this XXZ/TRS, and now that this correspondence between QQ systems and q-Opers in a sense goes even beyond that, because the space of solution, like we can write more general QQ systems. So QQ systems that arise in q-Opers, they contain set of these QQ systems as a subset, right? So, so in other words, like it's a more general integrable system than a quantum spin chain. And on Oper side, so as I showed you before, the a very sort of to get an integrable system, you need to pick a very simple Oper, and the space of Opers is much more complicated, and it says it contains the phase space of integrable systems as a certain subset over here. Okay, so that's one application, is the generalization of quantum classical duality. Okay, questions? I'm going to skip that slide. You can read this at home. I would rather talk about something else. Okay, so let's continue. Then the now, so that was SL2 SLN story. Now, what to do for any group G? Right, so let G be simply connected complex Lie group. And now we need to consider principal bundles. So let's FG will be a principal G bundle of a P1. Again, we have the same equivariant action. And now we'll look at certain, there is q-open dense set on P1, and then Q connection will be section of this sheaf over there. And then the, so that we choose the subset so that the restriction on the subset would be isomorphic to the trivial G bundle. And similarly, we would have A of Z, this Q connection, right? And then similarly, the change of trivialization will be applied in this case. Now, how would we do the Oper condition here? So how would we define GQ Opers for any group G? So we would have a principal bundle, and then the reduction on the Borel. So here I decided to choose B minus, kind of the negative Borel subgroup, reduction of this principal bundle on B minus. And the Oper condition can be written in this way. So here, so first fix a Coxeter element from the, which is the product of all reflections, right? Elements in the while group of G. And then, so take this product in any order that you like, right? And then the Oper condition would be this, that the restriction of the connection on this set U, like this would, so A, like in what was induced map before, right? So from L to E mod L now becomes this, now becomes the map from FG to FGQ. So it would take value, would need to take values in this double Brouillard cell, right? So you would take C, which is sandwiched with B minus of C of Z, where Z takes values in U intersection with MQ inverse of U. And so, so for example, in the simplest case, C, it will be just for SU2, it will be single reflection, and that reflection, if you like, it's it's interchanges between L and L hat from the previous slide. So like this condition for SU2 would be equivalent to saying that this is an isomorphism. Okay, and then locally we would write Q connection like this, right? We would take an element N and then elements N and N prime from a unipotent radical N minus, which is just a commutant of B minus with itself. And then in the middle, you would have some functions, holomorphic or meromorphic, phi I to the power alpha I check, which are the Cartan elements of your group of elements from maximal torus. Yeah, so that's how Oper condition works for any group G. Similarly, we can introduce Miura GQ Opers by giving a second reduction FB plus, where FG, A, and FB minus were meromorphic Oper from the previous slide, and this reduction is FB plus reduction is preserved by the Q connection A. Then you need to be careful about those two flags, FB minus and FB plus. So that should be in what is called generic relative position, and this is how it's done. So we choose the trivialization so that some point X, right, or we call it Z, but let's call it X now. So FG at X is isomorphic to G, right? This is torsor, and then under this identification, under this isomorphism, the FB minus of X will be identified with B minus multiplied by some element A, right? And then FB plus will be identified with B plus multiplied by some element B. And then the condition will be that so naturally A inverse B will take value in this double quotient, which is identified with a while group of G. And we say that these two flags are in generic relative position if this element here that assigned to the element of the while group assigned to them at X is trivial, right? So in other words, this A minus B takes values in this, I know, broad cell for C equals to 1 for element. So here you just put 1, right? So it's a trivial, like the big a big Bro cell. Okay. Questions?
So is the G just an arbitrary reductive group or is specifically SR2?
No, any.
Okay.
Yeah, so the condition that it's yeah, so it's simply connected algebraic. Yeah.
Okay.
Yeah, so that's important, right? So we'll talk how and it also doesn't matter simplaced, non-simplaced, it's type independent. Yeah. So it's as generic as you can go. And then so you can prove two important structure theorems, saying that so if there's such an Oper, then this connection takes values over here, intersected with B plus. Again, so SIs are the reflections and alpha check are Cartan elements. And you can even write some explicit formula here. So if so you have some elements, some functions di to the alpha I check, exponential to some coefficient divided by those gems ei. So eis are the pot fruits, but in Chevalier basis, and alpha i's are maximal torus elements. And then you take the product in the same order as you did in the very beginning in the definition of the Oper. So similarly to the SU2 example, we can add singularities and twists. And it goes, and it goes as follows. So again, we'll consider a family of polynomials. Now there is a polynomial for each direction in a Cartan, right? So if R is the rank, so there are R of lambdas. And then, so those are polynomials, and we allow the connection to vanish, right? To become singular at roots of those lambdas. So, and then using structure theorems, you can show that the Q connection takes this form over here, right? So it's a sort of formal product like that. And then similarly, you would require the Z-twisted Oper if this connection can be diagonalized with an element from G of Z, from the loop group. And if it's a Mueller-twisted GQ-Oper, if the diagonalizing element lives in Borel. Right, so this is obviously a stronger condition, right? So yeah. Okay. Now, how can we compute anything with this, right? So this is where the sort of Plucker relations come at the rescue. So we will not study the entire group, entire Oper at once. Instead, we will sort of taking it bit by bit from the two-dimensional subspaces. So here's some summary of how this Plucker relations works. So we say we have an irreducible representation of G with highest weight, and then I take a line subbundle which is stable under line subspace which is stable under the Borel B plus, and then sort of the relations look like this, right? That's if you have two dominant weights, then the image of L lambda tensor L mu is here, goes like this, right? So it's L lambda tensor V lambda tensor V mu into V lambda plus mu. So you simply just add the weights together, or you can sort of map it backwards. So if you have a collection of lines which satisfies this relation, then you can always pick a certain Borel subgroup in G such that this line L lambda is stabilized by B for all weights, for all weights. And then in sense, the choice of B is equivalent to the choice of that B plus structure in the previous definition. So this is like a motivation why we need this, but this is what we're going to do now. So we'll take so that line will be the one-dimensional subspace which is generated by the highest weight vector. So let's say nu sub omega I will be the highest weight vector. So it generates this line. Yeah, so this is highest weight relative to H inside B plus. And then we consider this two-dimensional subspace generated by this vector and then acting with the lowering generator Fi on that vector. So its weight will be omega I minus alpha I, right? Because it's simply doing one reflection in the root system. And it's spanned by this thing. So thereby we're getting a two-dimensional subspace, which is spanned by these two vectors, which is by construction a B plus invariant subspace of VI. Okay. So as an intermediate tool, as an intermediate step, we introduce Mura-Pluker GQ Opers. So essentially, it's an SO2 piece of the which corresponds to this two-dimensional subspace. But because it's only a subspace, it kind of talks to the rest of the structure. So this is how it plays out. Again, it's the same definition as before. We have the same data, right? We have those singularities if we need. But then so it's like so we have associated vector bundle V sub I, which is this thing. So it's FG cross over G with VI, right? So VI is, I remind you this, the vector space generated by, it's a line generated by the highest weight vector, and WI is the two-dimensional, it's a associated rank 2 subbundle. So there's a line subbundle and a rank 2 subbundle. And now we think of those guys as L and E in the definition of SL2 Oper. So we will define this Mura-Pluker GQ Oper. In fact, we will define as many of them as rank. So they carry index I. So it will be similar upper triangular matrix. But now it looks a little bit more complicated because, if you say have your, pick your favorite group or the algebra. So let's say do, 5, we can do E6 or D8. So you would say, for example, here, you would take, so you want to write it down for this node, right? So then we have, it will talk to 3 other nodes, right? And this will be reflected in this product over here. So you can do it for every node of the Dynkin diagram of G, right? So and then we define the Z-twisted Mura-Pluker Oper is this meromorphic Mura Oper on P1, such that, so the only thing that we're requiring is that the restriction, so if we take, so this guy here is the full GQ Oper, right? The stuff that we want to understand, thing that I defined before. So, and we demand that if you restrict that onto this 2D subspace, that gives you the Mura-Pluker one, right? So in other words, we're doing this restriction everywhere, and now our goal is to patch those pieces together. Okay.
So are the VIs two-dimensional, or they contains one? VIs,
yeah, correct. ZI, yes, thank you. The
VI, the VI.
So those, again, the VIs will be two-dimensional vectors. Yeah. So these are sections of VI. Yes, thank you. That's
so
right.
the WIs are rank 2 bundles, sub-bundles.
Correct. That's right.
And
yes,
the
exactly.
LIs are the sub-bundles of WI. Am I correct?
Mm-hmm.
Okay.
Yes, that is correct. Yeah. It's basically like it's a kind of taking a SO2 piece and kind of embedding it in every possible place like this. Okay. Now you can play the same. So you can specify this Oper condition, as I hope I explained for SL2. Right. Remember that the wedge product, the 2x2 determinant, and now it will lead to a more complicated relationship, right? Because you have these guys that talk to each other, to other nodes in the Dynkin diagram, and then there'll be many of them, as many as rank. So you can show the following, that if you spell out all these Mura-Pluker conditions, you will end up with a system of coupled coupled equations, which we call QQ system. So now pretty much it looks similar to what you saw already, except that these twist elements, they have these guys, right? So they also talk to, so AGI is the Cartan matrix of your root system, and the right-hand side is looks a bit more complicated. Yeah. So that shows you the kind of intermediate step, right? So we have proven that the sort of, if you follow this this idea, is that the space of non-degenerate, okay, so yeah, so space of solutions of the Z-twisted Miura-Pluka opers in the presence of certain non-degenerate conditions, which let me skip those, right, is in one-to-one correspondence with the space of solutions, again, in the presence of some non-degenerate condition of that QQ system from the previous slide. So non-degeneracy simply means that the roots of those polynomials, they're not, not equal to, so if U and V are roots of the polynomial, they're not, they don't belong to the same Z lattice, to the same Q lattice, right? Otherwise, there will be some cancellations in the formula and things become more complicated, but you can also work them out. Okay, and then again, similarly to the SL2 case, you can write those QK systems as systems of beta and Dutz equations. Now they couple together. It's a more complicated sort of generalized XRD spin chain. So we have proven sort of these two links using this Miura-Pluka connection, Miura-Pluka construction. So associated rank 2 subbundles and rank 1 subbundles, and then imposing Oper condition on those. So what we need to do now is to show how the bona fide Z-twisted Miura opers without Pluker. So we need to drop Pluker, fit into the picture, and basically show that there's an isomorphism here. Okay.
I try to understand the couple equation, some of the, or this, the AIGS or the Cartan matrix of the group.
Yes, yeah, AGI Cartan matrix. So negative means if it's off diagonal, see here, it's J bigger than I.
Right.
So it will be positive. It will be positive.
And the,
yeah, so,
theta Gs, what are the theta Gs on the left-hand side?
Theta, oh, zeta, right. So these are the these are the elements of the yeah. So those are, so Zi here is diagonal matrix like this, right? So it's a Zi to the power alpha I check. So that's
okay.
That's Zi.
Okay.
Yeah.
Okay. Thank you.
Sure. Other questions? Okay. Good. So yeah, I'm kind of already over time. So let me finish with this part, and maybe I can briefly describe the other applications. Okay, we talked about SL2. Let's skip that. Now, and here's the tool that will allow us to connect Pluker opers and normal opers. So again, Pluker is a rank 2 piece as opposed to the whole G oper. So you can there's this thing in literature which is called Langlands transformation. I'll be using some quantum version of it because everything is Q here. So you can show the following thing. So as you can twist the Oper connection by this element here. So if mu is some rational function and f is the lowering generator, then if you twist it like this, you'll get a different Oper, which looks exactly like the one that we had before, except that you switch the ith Q plus and Q minus, and then do some discrete transformation on the Z, on the twist element. So in other words, you would have a collection of yes, like after applying this transformation, you would have Q minus instead of one of those Q pluses. And then you can imagine you can do it over and over again. So it reminds, if you're a cluster person, a cluster variety person, like you would do mutations in your cluster, right? And it's in fact very similar to that. And my sort of second part is also of the talk discusses these mutations. And now imagine you're doing so the strategy would be to successfully apply those Bechdel transformations according to the reduced decomposition of the while elements. Every time you do this, it's like making a reflection, because you see what you're doing here. You would you would alter the choice of the Borel subgroup. So your B plus, like say B minus inside G, you would, as you do that, you're doing one simple reflection, and that simply means that you're picking a different Borel, right? So you would do the one reflection, and so what was positive part now becomes negative, and so on. And as you can understand, there's a handful of those transformations, so you can apply them one by one until you get the longest element, which you call W0. And as you do so, you can show that actually you would kind of align all the pieces together. You'll have the entire kind of Oper can be built out of this two-dimensional pieces, this Blücher Opers, and everything is consistent. So it's a technical proof, which I don't have time for. So it's based on properties of double Brea cells, and so it's a interesting algebra. And then it addresses the existence of this diagonalizing element V of Z, which, well, I can write it down for you. It's all it has an interesting formula on its own. So all in all, after the dust settles, we can prove that every Z-twisted Mura-Blücher GQ Oper is also a Z-twisted Mura GQ Oper, which connects establishes this connection here, and therefore this connection over there. Okay. Yeah. So notice that it works for any type of root system. It doesn't have to be simplaced. There's no problems. So it's type independent. It always works. Okay, now, yeah, so maybe for SLN, since for SLN can write everything very explicitly, you can do the following. So that element V, right, that diagonalizes Oper to a diagonal element looks like this, right? And then, so remember I told you that you can do mutations, those Berkeley transformations on each node over and over and over again. So if you do them, you would start generating new polynomials. So you start off with a Q plus, and then you have a Q minus. And then as you keep going over and over, you'll actually get other polynomials, which are not present in the original QQ system. So, and yet they'll be different. We can understand what they are. We can write relations on them. They look very much like the original QQ system, and it's called the extended version. And this kind of had a certain triangular structure. So if you start off with QR, like with the last one, you can mutate all the way to the first one. So it will be R of those, and then it will be R minus 1 for the next one, and so on and so forth. Yeah. So along the way, you also prove here that this correspondence between Opers and QQ system does not depend on the choice of order of elements in the element like W0. You can pick them in any other way you like. The Oper itself will look different, but the correspondence will still stay the same. Question? Okay. Yeah. So in other words, in this SLN description, I'm going to skip this. So so for SLN, you would define it like, instead of just having so if you want an independent SLN definition, you would just keep a flag of subbundles, right? So there's L1 inside L2 inside L3. So always you jump in dimension by one, in rank by 1, and then you would impose those isomorphisms on those factors, like Li mod Li minus 1 is isomorphic to the Li plus 1 over Li Q. So if you like, these are like analogs of those Mura q-Opers on each step, and then you can run the whole program, right? And then you'll find that there's some relationship which look like a quantum Wronskian relation. So it will be basically, if it's SLN, it will be n plus 1 by n plus 1 matrix, whose components are those Q polynomials over here, as well as the shifted Q polynomials by various powers of Q, and multiplied by various powers of twist parameters. Okay. Good. Okay, so I have one more story, but I'm not sure how patient people are. Maybe you can take questions now. And
So I don't understand. Do you want to move that story into the discussion part, or you want to explain?
no, I was asking, are you ready to listen for like for 5-10 more minutes, or do you want to end it now? Depends. That's what people want. So I don't want.
It depends on what the story will be.
Well, it will be connection to so this generalized minors. This paper by Fleming and Zelevinsky, fundamental relations in cluster algebra, and then how Opers arise in this sense.
I see some theorems in this part.
Yeah, you guys, you can look at the slides, right? You have the slides. You can basically scroll down.
Yeah, generate. So maybe indeed, maybe it's better to take questions now.
Mm-hmm. Yeah, let's take questions first, and then I can maybe make a couple of comments. Yeah.
All right. So, are there any questions? Actually, I kind of missed maybe an important point. You gave that example of monodromy data on the puncture torus. Yeah. Which I even don't remember what the integrable system is, but it doesn't matter because this is a geometry. All right, you can name it Calogero or not. Anyway, it's a cluster variety. So, and you mentioned for this QQ system, why you just do not kind of use why you cannot what's in new, are there any new statements about cluster varieties, or can you just go into the monodromy data from q-Opers to transform everything to the language of cluster varieties just by this Riemann-Hilbert correspondence for q-difference equations?
So I have something to say about cluster structure, but I'm not sure if it will satisfy what you're asking. So I don't know much about how Riemann-Hilbert works in this cluster story. So I heard some of your talks, Jan, but I think those were about something else, right?
But okay, but in a different language, you have some q differential operator, because ordinary Opers basically just differential operators, and so q-Opers is just
difference operator.
Q difference operator. Okay, good. So then you can go to the monodromy data, whatever is it, and it's something which probably in this particular example of Calogero-Moser is just local systems on the puncture torus with prescribed local monodromy about this puncture, which is given in your case by the diagonal mate. All right, and so then kind of if you believe that every differential equation with some extra conditions, it's the same as its monodromy data, maybe in some generalized sense.
And then
you can forget about q-Opers as q difference operators and just speak about monodromy data. And are they cluster varieties? And if yes, then why don't you kind of formulate all the results just in terms of the monodromies, because cluster varieties, it's industry, a lot of results are proven. Why do you need this Q, Miura transform and other things if there are mutations, and kind of why you don't just translate everything to the world of cluster varieties and forget about Q difference equations. Why do you need Q difference equations?
Because I like them.
No. There should be kind of more serious reason.
No, but like, okay, so I have connection to cluster literature in a different context, not in the, so asking the monodromy of this difference equation on the bottom, right? So like differential equation basically have something like this, and then yes, so it has basically, you can talk about it, Stokes phenomena, right? Or some asymptotic data, and then there's a cluster structure there. Is that what you're saying? So
Yeah,
I don't know. I have not studied that part. But we studied something similar, which leads to q-Opers, and that's what this first thing about ODEIM is. So here you would study asymptotic data, monodromy properties of some other equation, which is actually differential equation, which is also an Oper, but it's a different kind of Oper. It's what is called affine Oper. And then you can ask yourself, what's the structure on what is the monodromy structure of that? And the answer is it's the q-Oper. So essentially the monodromy matrix of that ODE gives you the Q connection. Okay,
yeah.
To be more precise, okay, I'll show you the formula. So it would look something like, where is it? Come on, there's some theorems. I didn't delete it. Yeah, there. So you would have, so imagine your equation has, say, k Stokes sectors, right? Like the different k asymptotic regions. And then like you would have and then now imagine instead of this S, you have A, the Q connection. So you would have the product A of Z, A of QZ, and so on, A of K, KZ. And that will be equal to the full monodromy matrix of that, of the ODE. Yeah, so there's that. Now you're saying I can find cluster structure in this, or?
You say that if you start with ODE, you recover this q-Opers inside of the monodromy data? Or
Yeah,
what?
yeah. Yes, that's right. So let me show you. It's a different
Okay.
talk. It's a different talk that I gave at Rutgers a couple of weeks ago. So basically, this typical example, you can take, this equation, which of course you can rewrite as a matrix equation, whereas basically you can write it as like this, like it's a Oper connection, and now, but now it's an affine Oper because there is this E0 contribution. There's an affine root, but it's an Oper. It's not a q-Oper. Okay. And then you would look at fundamental system of solutions, right? So now because it's an affine Oper, there's a affine structure. You can rotate the Kac-Moody parameter, and that will interpolate between different solutions in this in the space of fundamental solutions. And what you're doing is the following: you would and then basically you can, the theorem that you can prove is this: is that the where is it? The matrix here. So the monodromy matrix of that ODE is
what is Q in this?
Good. So good. So Q is the following thing. Let me show here. So Q is So I'm gonna write it down. 1 second. So let me. Okay, I'm gonna. Where's the form? It's related to the degree of the thing. So here, give me 1 second. I'll show you the Q. So if the potential is x to the 2m minus e, right? Then we're looking at Lie algebra with a dual Coxeter number x check. Q is something like e to the 2 pi I h check divided by m plus 1.
Hmm.
So it comes from the potential of the equation.
Yeah, okay. All right. Yeah.
But you see, as you're doing the monodromy around x equals 0, right? You get some factor here, and then you need to change this parameter e, which is like a spectral parameter, so that the whole thing transforms uniformly. And this overall coefficient you then sort of reabsorb by the rotation of the loop parameter in the Kac-Moody algebra. And that's in the Oper world translates into the Q equivariant action. Okay, that's the explanation.
Mm-hmm. Yeah. So
Does that make sense? Or?
Yes, it makes sense. Yeah, you see, I'm kind of, I understand that you like Opers, but I'm kind of a little bit concerned that in the world of Q difference equations, there is kind of the both sides of the Riemann-Hilbert, they are very closely related. It's kind of, they are both of multiplicative nature, although you can write Q difference operator, because a relation between two basic generators, like shift by Q and multiplication by the variable, it's like xy equal qyx. It's not, it's multiplicative, and therefore, from the very beginning, you somehow lives in the multiplicative world on the drum side, and so on the Betty side, it's more or less the same. So if you upgrade to elliptic, there will be almost no difference between the Ram and Betty. Like, you can consider elliptic difference equations, and they are monodromy data, and it's very difficult to distinguish which one is which. So that's probably what you meant when you mentioned that in Q Langlands both sides are a kind of.
Yes, that's right. Yeah, it's like it's same kind of category, same kind of objects, just the level is changed, right? I think it's something like kappa goes kappa goes to 1 over kappa h or h check, something like that. Yeah, I don't remember.
Yeah, actually, for people in the audience, maybe it would be kind of more pleasing to understand the monodromy data in terms of the Fukaya categories, because yeah, but I don't know. I mean, it's a different story. All right, thank you. More questions? All right, probably people are overwhelmed. And so,
if you guys want, I can send you these notes as well.
yes.
Yeah.
Okay, good. Sure. It's a part of the discussion session, yeah. And so we can attach them. All right. Anyone wants to make any comments? Well, if not,
actually, sorry, yeah, I always try to find them to unmute myself. Yeah. I'm going back to the definition of the Q connection, and
yeah.
So some of the basic, that's the page 4, I believe.
Yeah.
Here. So the EQ is that the pullback, but under the MQ.
It's a pull. Yeah, that is correct. Yes.
So given this here, what I'm a characteristic P person. So the monodromy, the MQ acting on the base. So in case of a characteristic P, I could have the Frobenius. This is what I was thinking during your talk. But the Frobenius may not be necessarily invertible. It's a one direction. But the Q gauge transformation, which gives some
you might like
sort of the Frobenius state conjugation.
A may not be invertible. I see.
A can still be invertible, and but the gauge transformation, for example, in the characteristic P case, I could just raise Z to the pth power, which can still be invertible. So does this make any sense in the setting?
I mean, like, will the formula allow? So say again, so it's q equals. So it's a certain choice of q, like the Koroteev, or.
Yeah, in this case, my q will be the p to the power of a prime p.
What is the base? What's the power? So p is the prime, and
P is a prime number. That's the characteristic of the field.
and then it's like n to some p, or
That's
what?
right. Yeah, the q the q acts on z will be raised p to the p to the rth power.
Yeah, I think as long as it's not a root of unity or absolute value is 1, it should be fine. I think. Yeah, like I don't see any immediate
so the
problems.
Frobenius is acting on the p1. And
yeah, I think that that
should
should do, like, looks like all the constructions should survive, I think.
Yeah, that's what I was feeling. Okay.
Okay, you were worried about invertibility. It should be okay. I think it should be okay.
Oh yeah, that part can still be invertible because through the gauge transformation, everything is preserved. So I don't have any specific models of even when n equals 1, what's the gear 1. So what the moduli space of these connections or the Opers would look like in this case.
No, if q goes to 1, if n is 1 and q is 1,
when
right?
n equals 1, the rank 1 case instead of rank bundles. So those are the simplest examples.
So you mean like for GL1 or so? Like
GL1 that would be the first toy model to look
but
at.
then I'm not sure how to define the Oper structure. It doesn't have any sub-bundles, right? Non-trivial continuous.
Oh, I see. So in order to do that,
in a sense, this is the minimal example, because I need to have something like my L should be, sub-bundle of E.
I see. So the Oper structure, it's kind of defining the kind of a parabolic, the Borel subgroup.
Borel, yeah, that's exactly, that's what I'm doing. Yes, like basically you fix Borel inside G. And what they call Miura Oper is a choice of that Borel. So instance, think of Oper as all possible Borel subgroups, right? And then you can sort of do the reflection between them. And Miura is a particular one. So for particular choice of the subgroup, you can write down this difference equation that we were discussing with Jan. And then if you take a different Borel, you can have a different Oper. So
in the cases of a GRN Oper, so instead of choosing only one single non-bundle, but choosing a flag.
You choose, that is correct. You're choosing a flag over here. So you would have, like the, L1 inside.
I see.
And so on, inside E, the full one. And you would impose this on every embedding.
So the next one is the Q twist of that.
That's right. Yes.
Okay. Now I got the figure. Yeah.
And that ensures
slowly. I was digesting slowly.
Sure. And that ensures that the connection matrix will be, where is it? Upper diagonal. I think
upper
I had it
triangular.
somewhere.
That's right.
Upper triangular.
And not only upper triangular, but also the twist.
Yeah. Okay. So here it's not the A, but it's basically, so in certain choice of the roots, A would look like this. It's basically you'll have the diagonal, the super diagonal, and everything else is 0.
Yeah. Okay, well, thank you very much. Now I got it.
Of course, yeah, no problem.
Okay, more questions? Well, if not, thank you, Peter, for the talk. And this is.
I know, Jan, do you have some time to talk after, or do you need to go somewhere?
No, maybe not now, but we can.
Okay, sorry, we can agree on that. Yeah, sure, sounds good.
We can exchange emails and talk separately. Okay, thank you.
Of course. Thanks, guys. Bye.